In this problem, we're going to test the significance of a correlation. In a previous problem, and from the Chapter 6 homework, we looked at a set of test scores that tested mechanical aptitude. We looked at people's mechanical aptitude, how well they could put pieces together at time 1, and then we used another test later to see if they were still correlated, if the tests were measuring the same thing, and it turned out that they were. They were very strongly correlated with, I think, an R of 0.98. Now in this problem, we're not going to just calculate the correlation, we're going to see if it's significant. Is it beyond what we would expect by chance? So you can copy the data from this problem 13.24 from your Chapter 6 homework, or you can type it in yourself. I'm going to copy it here. We've got this table where we've got the two trials measuring their mechanical aptitude at time 1 and time 2. And what we want to do is we want to calculate the correlation, but this time we're going to we're going to go to data, data analysis, and instead of using correlation, we're going to use regression. And this is where it's going to spit out lots of numbers and we have to figure out the right ones. So I'm going to choose regression. And it asks me for the Y input range. So I'm going to choose this entire table. I go Control-Shift down to choose everything there. That's, oh, wait. That's, no, I don't want that. I choose the entire table for a correlation table. For the regression, we don't do that. So let me delete that. The Y is going to be the dependent variable. Now, it doesn't matter which one, but I'm going to choose time 2, the G column, and the X is going to be the other one, the first one, the independent variable. And so we've got the two columns in the the X and the Y range. We've got labels, and the output range, I'm going to put that up here at, let me click in the box here, and I'm going to put that in J2. And I click OK, and we've got lots of ugly numbers. So let's go to Home, change the number format to number. That gets it down to 2 decimal points. Let's make that first column wider so we can read what we're doing. Now let's figure out what one is the most important. Now this multiple R here, I'm going to, this is the correlation R. That's really important. This down here, this observation, this is the number N, so we need to pay attention to that. Now, to find out if this correlation is actually just the absolute value, so I'm going to put the absolute value sign around here, because this capital R means it'll always be positive, so we have to look elsewhere for the let me get the italics correct there, and that looks a lot nicer. We've got to look for the sign somewhere else. Now the significance, the p-value, is this significance under this ANOVA here, because that's the test that it's using. And this is our Control-Z. Let me go back here. I will label this as two-tailed p value, and it's 0.00. Now probability is never 0. There's always a little chance of it. So if we were to add lots of decimals, we would eventually get something there. So you don't want to report p equals 0. What we want to do is we want to report this as p less than 0.001. Now for the sign, we need to look down at this coefficient here of our first variable, and that's going to be our sign of the correlation. So because this is positive, that means the correlation is going to be positive. Now, another thing that we can do is we need to report the degrees of freedom. Now, in correlation, the degrees of freedom is n minus 2, so we know it's going to be 10, minus 2 is 8, but also we've got the degrees of freedom reported here. This residual degrees of freedom is the number of degrees of freedom in the correlation. So now we have everything we need to report our answer. So we can put it in APA format and complete sentences and say our hypothesis that the scores on 2 tests are correlated. Now notice how our hypothesis was simply that they were correlated. That means it's a two-tailed test. So we're going to use this two-tailed value there. Now we could have made a one-tailed test, but the book said don't assume anything. They might be really bad tests. So we didn't assume anything, and so that means a two-tailed test. So we'll use the two-tailed p-scores. So our hypothesis that the scores on the 2 tests are correlated is supported. Let's put the APA in that same sentence. I'm going to put comma, and then I'm going to put the relevant statistics in the next line. We want to report R in italics, Control I, R, Control I, and then immediately after the R in parentheses we put the degrees of freedom, which is 8, and then space equals space 0.98. I'm going to put a comma, space, and report the p-value. The p is supposed to be in italics, so Control I, P, Control I, space is less than, we're not going to say what the p-value actually is because that's just too many zeros, is less than 0.001, and we should report that this is 2 tails, period. So that's how we report our hypothesis in the results in the APA format. These are strongly correlated tests. They really seem to be measuring the same thing, and the reliability over time seems to be legit.